Welcome you all to this new lesson of circuit theory. Today we'll be discussing about mesh analysis or loop current method. This is a powerful tool frequently used in determining current through a particular branch or voltage across a particular branch of an electric network. As I said in last class, there are different tools for determination of current or voltage for a particular branch of an electric network. Uh, Based on the applications of this analysis tools, sometimes a particular circuit is suitable by using mesh analysis method uh, for its calculation purpose. Sometimes nodal analysis method is suitable for calculation of current voltage for a particular branch of any network. So it is needed to be known to us, it is to be identified which network analysis tool is to be applied where. Today we'll be discussing about mesh analysis, which is purely based on application of Kirchhoff's voltage law. In last class we discussed about nodal analysis, which was based on Kirchhoff's current law. So if an electric network is having current sources with it, it is preferred to use nodal analysis method. If a circuit is having voltage sources, multiple voltage sources, multiple loops, in that case, mesh analysis method would be suitable for calculation purpose, for analyzing purpose. So today we'll be discussing about basics of mesh analysis, different explanation of steps. Those steps will be followed later to solve numericals to analyze electric network. Then we'll be discussing about concept of super mesh. If a circuit is having current source and we are asked to uh, solve the electric network using mesh analysis, so how can we deal with that current source? What is the concept of super mesh? All those will be discussed today, and later we'll validate explanation of steps, concept of super mesh, all using some examples. So let us start with the basic concept of mesh analysis. As like nodal analysis method or Kirchhoff's laws, current divider, voltage divider rule, this is another network analysis method which is used to determine voltages or current for a particular branch, that is which is used to determine circuit variables in terms of loop currents. So what are loop currents, that I'll discuss later. In case of nodal analysis method, circuit variables were determined using in terms of node voltages. So what were node voltages, that is hopefully clear to everyone if you have gone through the last lecture. Today we'll be discussing about mesh analysis, which is another powerful method for determination of circuit variables in terms of loop current. So what is loop current, that I'm coming into. Nodal analysis method was based on KCL, but loop analysis method or mesh analysis method is based on KVL, Kirchhoff's voltage law. Now, these are the steps which you should follow in order to determine current through a particular branch or voltage across a particular branch using mesh analysis method or loop current method. So first step is identify and mark all the mesh. First we need to identify the mesh or loops, then we have to mark all the loops. Next point is assume current in each mesh. Loop current is to be measured, assumed for your better understanding, to avoid mistakes in calculation, or to not to get confused regarding assuming loop currents in which direction it is to be assumed. Let us assume clockwise direction of current all the time. You may assume anti-clockwise direction. It would not affect your result. But for better understanding, to avoid mistakes in calculation, let us assume clockwise direction of current for each loop all the time. Next step is current through a common branch of two mesh is subtraction of mesh current. If we assume clockwise direction in all the cases for all the loops, then current through a common branch will be subtraction of all subtraction of mesh currents. Which two mesh currents? In between the in between which two loops the branch is common, mesh current will be subtracted of those meshes. Apply KVL in each mesh. We'll have to apply later KVL in each mesh or each loop. Replace KVL equation in terms of mesh current and find the solution. This note I will discuss later. Let us discuss these steps with the help of one example. See, here first we need to identify, as per step 1, we need to identify all the mesh or loops. So see here, A, B, C, and all these are same nodes, so E. These are 4 nodes. Now there is one loop which is A, B, E, then again A. There is one loop, this one. There is another loop, this one, which could be written as B, C, E, and there is another loop which is the outer loop, this one. So there are 3 loops. Concept of loop is already discussed in basic classes. So the outer loop is A, B, C. This is the outer loop. So there are 3 loops. Now, so first we have marked all the nodes to identify all the loops and mark all the loops as we marked all the loops as A, B, E, A, B, C, E, B, or outer loop as A, B, C, E, A. Next step is, step 2 is assume loop currents in each loop or each mesh. For your better understanding, as I said, you always consider clockwise direction of currents, clockwise direction of loop currents. So there are 2 loops for loop 1. For loop 1, we have assumed I1 as loop current, I1 as loop current, and it is assumed in clockwise direction. For loop 2, I2 current is assumed, which is again in clockwise direction. So step 2 is over. Now step 3, current through a common branch of 2 mesh is subtraction of mesh currents. So what is that? See, for these 2 loops, for loop 1 and for loop 2, for loop 1 current is I1, for loop 2 current is I2. Now R3 branch is common of these 2 mesh 1 and mesh 2. Now what should be current through this branch? See, I1 current is flowing like this. Through R3, I1 current is in downward direction. But through R3, if we consider loop 2, see here, I2 current is flowing in upward direction. So what should be resultant current of R3? Current through R3, that is I3. I3 should be equals to I1 minus I2, or it could be written as I2 minus I1. As I1 and I2 are assumed current, we still need to find the values of these currents. So we cannot say which one is exact equation, I1 minus I2 or I2 minus I1, isn't it? If you know that I1 is greater than I1 minus I2 will be valid. If you know I2 is greater than I2 minus I1 will be valid. So you don't need to think of this. You can write I1 minus I2 or you can write I2 minus I1. Whatever you want, you can write. But let us come to now this point, this note. While applying KVL in one loop, consider that loop current is greater than other loop currents. In that case, IR drop will always be negative. What does that mean? If we consider, if we are applying KVL in loop 1, if we are applying KVL in loop 1, consider this equation as the valid equation. That means consider I1 greater than I2. Similarly, if we are applying KVL in loop 2, consider this equation as valid. So if you assume, while applying KVL in loop 1, if you assume I1 is greater than I2, then your IR drop will be always negative. Similarly, if we work on work on loop 2 and applying KVL in loop 2, if you consider I2 is greater than I1, then also your KVL equation, in your KVL equation, IR drop will be negative. So what is that? We need some example to solve, to make better understanding of this. So as of now, I am leaving up to this. Later I'll discuss why IR drop will be negative. Okay. Step 4 is apply KVL in each mesh. So for loop 1 or for loop 2, we'll have to apply KVL. Once KVL is applied, we'll get KVL equation for each loop. So now KVL equation will be replaced in terms of mesh current, and we'll have to get the equation for solution for I1 and I2. So this is the explanation of steps. In next slide, we'll discuss about concept of super mesh, and then we'll move to one explanation. That explanation will make you more clear regarding the discussion of steps. So now let us discuss about concept of super mesh. Let us consider this circuit. Here for this circuit, there is a current source. So if I ask you to apply KVL in this loop, you cannot apply KVL in this loop due to presence of this current source. What is voltage drop across this current source is not known to us. So as per KVL, voltage drop in each element need to be known. That is why KVL is restricted for this loop due to presence of this current source. So what can we do here? We can consider this as super mesh. Now, don't get afraid of super mesh, because calculations involved in super mesh or super nodes is much easier than conventional calculation. How? See, you may apply KVL in this equation, in this loop. So KVL equation will be 10 minus 4 I1. See, this is your direction of travel and this is direction of current. So as per direction of travel shown by blue, As in KVL, I told you to mention clockwise direction of travel for all the time. So this direction of travel implies there is rise in potential for 10 volt. So it will be plus 10. Similarly, as direction of current I1 is in clockwise direction of travel is also in clockwise direction. So through 4 ohm, voltage drop will be 4 into I1. I1 current is flowing through 4 ohm. Now voltage sign of this voltage drop will be minus, because direction of current and direction of travel both are in same direction, which implies, as per KVL, which we discussed in sign convention of IR drop, if direction of current and direction of travel both are in same direction, IR drop will be negative. That is why we have put it negative. Next, let us come to this note. While applying KVL in one loop, consider that loop current is greater than other loop current. In that case, sign of IR drop will always be negative. Now let us understand this point. So KVL equation will be for this loop, KVL equation will be 10 minus 4 I1. This is our direction of travel. Okay. Now if while we are working with loop 1, as mentioned in that note, while working with one loop, consider that loop current as greater. So if we consider I1 greater than I2, current through this 6 ohm common branch will be I1 minus I2. Okay. Now voltage drop across 6 ohm will be I1 minus I2 into 6, because through 6 I1 minus I2 current is flowing. Now as we have assumed I1 is greater, which implies I1 greater means current will be flowing in the direction of I1. Okay, so resultant current I1 minus I2 will be flowing in the direction of I1. Direction of travel is also in clockwise, and direction of this I1 minus I2 will also be in clockwise direction, as I1 is assumed greater in this case. As I1 is assumed greater, so direction of current should always be in the direction of I1. So as both direction of travel and direction of this resultant current is in same direction, in clockwise direction, so IR drop will be negative. So what can we conclude from here? If we work on one loop, if we consider that loop current greater, then resultant loop current will be in the direction of that loop current, that is in clockwise direction. So direction of travel and direction of current through the common branch will be same, which implies uh, minus sign of IR drop. That is why I've told, if we work on a particular loop, consider that loop current greater. In that case, you'll always get minus sign for IR drop. This equals to 0. Okay. Now see, for super mesh, what can we write? This is I2 and this is 5. So I2 can be written as minus 5. This is I2 and 5 is in opposite direction, so I2 should be minus 5. So substitute I2 value here. You have only I1 unknown. From this equation you get solution for I1. So this concept of super mesh will make your calculation more easy. Now this was the case if current source is involved in any one loop. If current source is involved in both the loops, that means in the middle branch or common branch of two loops, in that case what will we do? We'll apply KVL in the outer loop. We'll apply KVL in the outer loop. So in this outer loop, if we apply KVL, what will be KVL equation? See, in the outer loop KVL is applied, but current through this 6 ohm will be I1. So current through 6 ohm is I1 mentioned. This part is omitted from this, but you need to assume that there was one super mesh element, and due to these elements are excluded here, but I1 current will be flowing in the left of this dotted line, and I2 current will be flowing in the right of the dotted line as shown here. Okay, now what will be KVL equation? 20 minus 6I1 minus 10I2 minus 4I2 equals to 0. Again, for this element, what can we write? If we apply KCL at this node, I2 equals to I1 plus 6. So I2 equals to I1 plus 6. So I1 can be found in terms of I2. And in this equation, we can replace I1 by I2 to get equation for I1. And finally, we'll get I1, I2 both. So this is the concept of super mesh. Now let us solve this problem. First step is we are asked to determine loop currents I1 and I2. So our first step is let us mark all the nodes to identify the loops. So one loop is ABDA, that is loop 1. Another loop is BCDB, that is loop 2. So we have assumed two loops and we have assumed two loop currents, I1 and I2. Now for the first loop, what shall we do? See here, we have assumed as per step 2, we have assumed clockwise direction of current. Now next we have to apply KVL in loop 1. If we apply KVL in loop 1, what should be the KVL equation? 15 minus 5I1 minus 10. As we are working on loop 1, so I1, let us consider I1 greater than I2. Minus 6 equals to 0. You may specify branch currents or you may not specify branch currents. It is not needed. You may specify, but you may not also. Now let us check this equation. For loop 1, okay. See, here we have written plus 15 minus 5I1 minus 10I1 minus I2 minus 6 equals to 0. But it can also be written as minus 15 plus 5I1 plus 10I1 minus I2 plus 10. So it is 10. Okay, if we take common, a minus common here, if we take a minus common here in our equation, we'll get this equation. Okay, so whatever you want, you can do. So this is one equation. From by simplifying this equation, we'll get this one. Similarly for mesh 2, for mesh 2, we'll apply here apply KVL in second loop, 10 minus. Now we are working on loop 2, so let us assume I2 as greater. So this is the equation. By solving this equation, you will get this. Okay. Now we have two equations. Now these two equations can be solved to determine these two unknowns I1 and I2. So this can be written in matrix form to apply Cramer's rule to get the solution. See, coefficient is 3. So first we have written 3, then minus 2, minus 2. This should be minus 1. This should be 2. Why? Because by rearranging this equation, we'll get this minus I1 plus 2I2. So if this I1 is taken here and 1 is taken here, so this will be the equation. Okay. So from this will be del 1 and del 2 can be found like this, as we discussed earlier. So finally you'll get two loop currents, I1 and I2, 1 and 1. Now I1 is 1, I2 is 1. So what should be I3? I3 is I1 minus I2, that is 1 minus 1, 0. So current through this branch, common branch will be 0. So likewise, you can find all this current through 5 ohm will be I1. So that is 1 ampere. Current through 6 and 4 ohm will be 1 ampere. Likewise. So this is what about mesh analysis. So what we discussed here, we have discussed basic concept of mesh analysis. We have discussed the explanation steps involved to calculate current through a particular branch or voltage across a particular branch using mesh analysis. Next we discussed concept of super mesh, and later we validate explanation of each step with the help of one example. We also discussed when to apply nodal analysis, when to apply mesh analysis. If a circuit involves loops and voltage sources, then mesh analysis would be easier to use. If a circuit involves current sources with nodes, then nodal analysis method will be more suitable for such circuits. So as of now, here I am ending up the session. In next class, we'll be moving towards network theorems such as superposition, Norton, all those theorems. Before discussing superposition, Norton, all those theorems, we'll be solving some numericals on mesh and nodal analysis as well using AC sources. Okay. Thank you for today. We'll meet in next class again. Thank you all.